Cool. Hello. So to kick things off, my name is Chris Nesbitt-Smith. I'm based in London, currently work with some well-known brands like Learn K8's Control Plane and some various bits of UK government. I'm also a tinkerer of various open source-based stuff. I've been using Kubernetes in production since it was zero point 0.4, including some multi-tenancy environments. So believe me when I say it's been a journey. Definitely got the war wounds to show for it. As Mike said, we should have time for questions and, of course, your best heckles at the end. But if we run out of time, or if you're not watching this live, then please do find me on LinkedIn or indeed on the Loft Labs Slack, which I'm sure Mike could share a link to as well. Right, let's get going and stop looking at a big picture of my face. So we all came here in search of minimizing kind of wasted overheads in our computer estate, right? Okay, well, let's at least kind of go and with that and pretend it wasn't just an exercise in technical navel gazing and CV enhancement. So ideally, we'd want to isolate one workload from another. We'll want some super easy kind of use of managing all of those isolated things because we'll need all that collective spare time to think up exciting new abstractions of just how to basically run a process on a computer and invent a new job title to us. So shout out to my DevSecOps SRE platform engineers. And our ability to reduce waste on the hardware should give us some cost savings, which we'll all need to buy the Apple Vision Pro with some dev AR ops, obviously. So, how do we realize all of these dreams? Well, here comes the science bit. Kubernetes embraces the idea of treating your servers as a single unit and abstracts away how individual computer resources operate. So, if we imagine having 3 servers, you can use one of those to install the Kubernetes control plane. The remaining two rather, can join as worker nodes. Once that's complete, the physical servers are mostly abstracted from you. You can mostly just deal with Kubernetes as a single unit. When you want to deploy a container, you submit your request to the cluster. Kubernetes takes care of executing Docker run and selecting the best server for the job. The same happens for all the other containers. For every deployment, Kubernetes will find the best place to run the application. Out of the box, Kubernetes gives you namespaces. So if you have 3 applications or teams, you could create 3 Kubernetes namespaces and place one in each. And you'd probably be forgiven for thinking that namespaces might refer to a lower level of implementation of kernel capabilities and kernel namespaces that would kind of give you some kind of level of isolation. However, a Kubernetes namespace is just a logical partition in the cluster that is used to group Kubernetes objects together. It doesn't actually offer any isolation. It's just a convenient way to categorize or compartmentalize objects. And okay, yeah, you could say that it has some performance benefits for the scheduler in terms of limiting its scope when it's figuring out where to run stuff. So let's explore how we can apply namespaces, at least as a first go, since it's a useful baseline and we can see how many folk have done this in the past. At least before managing multiple clusters became a thing when we put down Kubernetes the hard way, well, thanks Kelsey, and remembered that we can at the very least script things. So how do we carve up the estate? Well, you could split up your 3 teams, or perhaps you could do it by lifecycle stage, so say dev, test, prod. But what about when your teams need multiple lifecycle stages? You start to see this getting quite busy. So how big is this probably likely to get for most worlds? So here's with with 10 tenants. The slides got smushed together, and one with 50. So assuming that they're all serving some HTTP traffic, you'll probably use an ingress controller, say Nginx, which generally operates as a single pod that can serve your, say, 10 tenants, just as easily as your 50. Notice how we didn't need to scale to have 30 ingresses for our 10 tenant cluster, or worse, 150 for our 50 tenant cluster. So what might be the cost implications of this sort of choice? Well, if we look at the Ingress Nginx Helm chart config, you'll see we've got a resource request of 100 millicores and 90 meg of RAM. So let's put scaling for the volume of traffic aside for a minute and just assume that we're just looking at the standing still cost. While the numbers might seem low in isolation, they're going to turn into paper cuts quite quickly. So our 10 tenants, 3 life cycle stage cluster is going to look something like this. And our 50 tenants, one looks even worse. But this is just math, right? Multiplication. And compute is cheap and maybe who cares? Well, maybe, depending on who you are, someone might care when they get the bill for your ingress node requirement without it actually doing anything real. You're at a baseline of $248 a month just to stand still before you even add any monitoring, logging, and all the other normal things that you run in your cluster. So a single ingress might look like a good idea, perhaps. But what happens when one of your Snowflake teams wants a configuration option that isn't readily made available by the ingress annotations configuration, such as, say, tweaking the keep alive? But others don't. Sure, you could use configuration snippets annotation to tweak this, but that's quite a blunt instrument. You shouldn't probably kind of give that to all your teams, since it allows any one of them potentially to break or manipulate ingress for everyone. So you're stuck having to define that configuration option at a full cluster level. Consequently, those that didn't want the configuration then had it forced upon them. If we look at our patent pending multi-tenancy meter, you'll see that it's tracking the configuration of a single shared ingress. Is tracking kind of reasonably nice and cheap. But let's face it, when was the last time that ingress was the only thing you installed in a cluster? Those custom resources won't define themselves after all. So something like this probably looks more familiar to you. Logos as far as the eye can see. After all, our DevSec FinOps CB needed something new and shiny added to it. So let's take Prometheus, for example. Well, you don't normally run it like this, where you have a shared one for every application workload. So your cluster is going to be looking something more like this, perhaps. Taking a look at, again, our multi-tenancy meter, we can see that the cost of this practice is accruing. So since we're a kind of logo-loving DevOps, let's see what more complexity we can add and manage it more easily, and give ourselves enough time to anxiously refresh the CNCF landscape for what new logos to find that we will obviously need to install in our cluster next. So the first tool we'll have is the Hierarchical Namespace Controller. We'll then look at vCluster from our kind friends at Loft Labs. The V stands for virtual. We'll look at more about what that means in reality, since whilst it's novel, it doesn't necessarily align with the word virtual that we are used to maybe seeing in other computing senses. And lastly, we'll look at Karmada as a means of managing many clusters. Okay, so the Hierarchical Namespace Controller, as the name suggests, is a controller that allows you to define a root or a parent namespace, and then define a child tree off the back of that. The rabbit hole can go as deep as you like. Okay, so this is the first of my 3 demos today, because Daniele and Salman, who did the previous 2 talks, thought it'd be really funny if I demoed all the hard stuff. So join me in my prayers to the demo gods whilst I try and not mess this up too much. Cool. Okay, so let's demo the thing. So it's the directory, just set my path right. I think I already got a cluster ready. Yeah, I did, fine. Cool. So we're going to apply the hierarchical namespace controller. We are going to patch it as well. I will show you what that patch is. So the reason for this is it runs out of CPU and starts crashing with what we're about to do. So all I've done is I've increased the CPU, and I think I increased the memory as well as a limit, which allows it to run a bit better. Right, so let me just check that that is now running. Fine. See, it's already had 1 restart, should have days. So let's go and create our parents' namespace. So indeed, kubectl create, so just a imperative command to do that. And then there is a extension with this, which is the kubectl ns bit of command that allows us to then go and create tenants within that parent. So you can see that the top namespace is just a normal Kubernetes namespace. The other ones have some more metadata on them. We can look at that in a minute. And then we can look at the properties of that, of the namespaces that are there. So we can see that the configuration looks like this. So we are propagating the role bindings and roles at the minute. So let's also propagate the resource quota, which will look something like that. And then if we run that describe again, we can see that we're going to be copying from the parent any resource quotas that we go and create in the parent will now be copied down into the child. So if we go and look at what that might be, we can see a resource quota here, which name is CPU quota. It's going to go in the parent namespace. Um, and what we should see, with a bit of luck, so if we do, just to show that it's not fake, so we can see what it is before. So there's the before. Now, if we apply that resource quota, with a bit of luck, if this works, cool. So we can see that it's in the parent, and by virtue of the hierarchical namespace controller in the configuration that we've given it, it's also made a copy of that into the tenant namespace. So happy days. Um, so what how big can this get? So let's have a look. So if we do have a look at this, we've got a bash script here because everyone loves bash, right? And I'm going to create another 49 tenants. So let's have a go at that. And you'll see that this runs quite quick, apart from when the hierarchical namespace controller fails and falls over. But let's work now, so we'll count our stars. So let's have a look. And we can now see that we've got 50 of these tenants that now exist. We can do some other things that if you want to delete the parents, it won't let you unless, so if I do say parents, it will say you're not allowed to do that because it's the parent one. But what I can do is I can allow cascading deletion, and then I can delete my parent, and it will go take a little bit longer, but it will go and trash all of the children. And then just for hygiene, because I'll use this cluster in a minute, I will also trash the. It's finished. Also uninstall the controller as well. Slow us down. Cool. Okay. Um, cool. So let's go back. So first demo done. Wasn't too bad. So as we can see, the namespaces aren't kind of fully nested per se. It's all just smoke and mirrors. Oops. So there's a single controller doing the templating work for us. But at the end of the day, the namespaces that are the tenant namespaces that are created are just regular namespaces. There's no magic fundamentally going on here. So a multi-tenancy emitter shows it's cheap since the standing still cost of all our tenants is still zero. Since we're not deploying any workload on them, we're just doing that resource config. These are all just empty namespaces, a construct that's basically just stored in etcd. There's absolutely no inherent cost associated with any of this. But what practical use might these namespaces have? Well, so if we have a look at roles, or as we saw with the resource quota, if one of our teams has some roles, they can then read and write pods, so maybe PVs, into the root namespace. We could cascade those role bindings to all of the children. And we could do the same for many teams as well, all allowing to access that PV. Okay, so our next approach of isolating the control plane which is what vCluster does, whereby a namespace is created, and inside that we run a small K3s instance. Those that aren't familiar with K3s, it's a lightweight Kubernetes distribution that by default uses SQLite as its database backend rather than etcd, and it can lend itself well to working very well just as running as a single binary because it ships with kind of everything that you'd need all in one thing. Okay, so we can hit the API server of that K3s installation with kubectl and create a pod. But this is just an API server. There's no nodes or anything else like that in order to run the workload. What's more, it's actually the wrong database for the real scheduler to pick it up. So what can we do about that? Well, we could copy the pod spec, which is which would then magically cause the pod to be scheduled somewhere on the parent cluster. And that's exactly what vCluster Syncer does for you. So it selects the resources and the direction to sync them in between your clusters. And with global resources like an ingress controller, CRDs can just sync the primitive resources like pods, config maps, secrets, persistent volumes, and so on. So if I apply my PV to the tenant cluster, it will get then stored in the tenant control plane and then synced to the parent and allow the PVC to bind to that PV and then, of course, the pods to be able to connect to it. Okay, next demo. Get the right way through this. Cool. So we've got a configuration that we're going to give it here, which is going to create. We're going to use to words to sync persistent volumes in our synchronization. That's the only thing that we're going to sync. So let's go ahead and create. So I'm still using Kind, which if you're not familiar is Kind as a Kubernetes in Docker thing, such as a local cluster that's running here, which is what I used in the previous demo as well. So I'm going to use vCluster, which is going to talk to that and create one of these tenants. So that's going to take a few seconds to run, where it's going to go and download some containers and boot that up inside. So that's using the config. I've created it called tenant1, and it's going to apply this config to the tenant config. Give that a sec. Okay, cool. And with a bit of luck, that should have also changed my config. So if I do, say, that should be probably, uh, I think, yeah, server is K3S1. Awesome. So I'm now talking to the vCluster. It's changed my Kubernetes context for me, which you see up here, right? I'm just fooled because I was doing this in Tmux, which hasn't then changed what's in the bottom corner of my screen for me to cue me to where I am. Okay, never mind. So, words. So, what do we do next? So let's cat the pv.yaml. So this is my persistent volume that I'm going to create. So if I create this persistent volume, I can do get pv. So I can see that persistent volume. That's within the tenant. Now if I do, if I disconnect from this, which will return my disconnect, will return my context. It doesn't actually change anything at all. Like on the cluster, all it's doing is changing my kube config back to pointing to the parent's kind cluster in this case. So I now do or key server, for example, version. That's what let's do. We'll see a difference. It's not showing that it's not showing that the version is K3S anymore. And what I can do now is if I do get PV, I can see the system volume is here where it's been created. So that was the one within the tenant. So I've got the ability to now see that in the thing. So I can do the same. I can go and create, say, another, just to do that again. Anyone that missed it? So let's go and create a second tenant. Should happen a bit faster this time now that the containers are in my local cache. Maybe, possibly. Hopefully. Because I'm about to boot up 50 of them in a minute. So hopefully this isn't quite so consistently slow. Cool. Okay. So we can now apply the persistent volume again. We do. So if we get the PV, we're still within the second tenant context at the minute. So we do, PVs aren't namespace dependent, right? So we can see that I've still only got the one that I've just created. So if you remember, tenant one also has a persistent volume attached to it. But the tenant two also now has one, but I can only see the one that I've created. So if I again disconnect, disconnect, and now get PVs, we can see that the one for tenant one and for tenant two are visible to the parent, but one can't see the other. So they're kind of isolated. One doesn't necessarily need to know about the other, but the parent cluster is still actually going to go and provision this storage somewhere where however it happens. Okay. So just for fun, we can demo what you can do. So I've got a thing here, so I could do that. What I could do, actually, if I wanted to be even more fun, let's do, let's actually make that do a bit more. Um, make it connect. Might be a bit slower, but we can run it anyway. Let's pause it halfway. So let's get it to apply the system volume and then vCluster disconnect. With the magic of some bash scripting, should be able to do that. And we can go and just do that on a loop, which will go and create as a new tenant, put a persistent volume in it, and then rinse and repeat until the cows come home. You probably won't bother watching that go for more than a couple, just to show the point that the things get synced around. There's tenant 3, tenant 4's coming up now. Of course, this was much faster when I did it. We're not showing a load of people, but it's fun. It's not bother waiting for all of them. Give them the fifth one, and then we'll kill it after that. Okay. So indeed, let's just make sure I'm not in the context of one of those. Cool. So I can now do, if I do kget namespaces, I can see there is a namespace for each of these. So the vCluster has created those. I can do uh, and I can see all of the inside those. It's created a instance of core DNS running, and it's also created the tenant of the API server that's running in that pod. Cool. Okay. Stop using this kind setup because the next demo doesn't use that. Awesome. So this kind of gives us nested control planes. With the sense that we can give what feels like cluster admin out selectively to tenants. If you squint, it's basically kind of like a virtual cluster. But there is a single parent cluster that does exist and can have controls and configuration set there. And we don't have heaps of fully independent clusters, all of which can be many highly available ones. So a multi-tenancy emitter is twitching, but it's still reasonably cheap to operate this way. So we'll need around an extra 17 nodes to handle all of our 50 tenant control plane pods and 50 PVs for all of the databases that exist, totaling out around $254 or $5 a tenant per month. But what does this mean for your workloads though, when you apply a pod? Well, the pods will share the same nodes as the other tenants, which introduces a noisy neighbor concern. But we could create pools in order to separate that. So a single control plane could conceptually operate multiple pools with vCluster, which makes this a bit easier with the node selector and enforce node selector options. So that all sounds great, but what about the network? Well, the inherent rules of Kubernetes networking still exist, that any pod can talk to any other pod, and that overarching cluster is still a flat network. So depending on your network, you may be able to apply network policy in order to limit what is permitted to talk to what, in effect giving us an isolated network boundary. vCluster makes this easy with the dash dash isolate parameter that behind the scenes goes and creates those network policies for you. So that gives us a kind of isolated network. But if any one of those containers does manage to escape the host, perhaps through a kernel vulnerability, and that black box was at some point an explosion image, but just imagine that that's there. I'll blame Daniele for screwing up the slides. So, well, you've then got to the node. And that's then obviously if you've got the node, it's not a big leap to then take the kubelet. And again, if you've got the kubelet, it's not then a big leap to then take the control plane, at which point your entire multi-tenancy cluster and everything that it connects to has been compromised. It's universally referred to as a really bad day. So what alternatives do we have left? Well, we could run a bunch of different clusters. So enter Karmada to help us make some sense of that, which abstracts some of the things that you might be used to seeing in Kubernetes with some Karmada equivalents. So to dig into the architecture of that a bit, our master cluster can command the child cluster's agent, which in turn communicates with the agent's cluster API server. So a kubelet applied to the master can cascade down into the child cluster. So this effectively gives us independent clusters with an overarching central management, with calls made to the manager being passed down to the child clusters, giving both standard and fixed workloads, perhaps maybe say some logging and policy engine and config, excuse me, along with workloads that are individual to each team or environment. And the child clusters could be anywhere from all being in the physical data center to all the way through to geographically disparate, multi-cloud, and some hybrid cloud being thrown in for good measure because, of course, fun times, right? So last demos, last prior to make some of the demo gods. So wish me luck. I can never remember which way to actually go. So I have a alternative kube config handy. Oh no, that is right. I'm connecting to the API server. Fine. So I can do, yeah, fine. So this cluster has 50 child workers on it. There's a CRD for cluster. Which is this one here, right? So it's that full as a complete CRD. So I can see my long list of worker nodes that are here. So let's deploy something onto a worker. So if we have a look at a deployment, we've got a thing here with one replica as an app. And I'm going to explain what this is. So I'm going to got the kube config of one of those workers, happens to be worker one. And I'm going to do kubectl apply to apply that deployment to that worker. So if I hit that, what I've done here is I've spoken directly to the worker to go and create that. So I could have given, this could be the kube config that I've given one of the tenant teams, right? And that this is the thing that they've got. And they've then got complete ability autonomy to go and manage the workload just talking to that cluster. But from the parent perspective of this control plane type cluster, I can run a command like this, which isn't the most user friendly, but I'll walk you through what it's doing. So Karmada gives you ability to search for things. So I'm going to search for deployments, and then I'm just going to pass the output through JQ, just to make this so that we can actually see the responses here. And what we'll see is we've got our hello world pod right here, right? So that was the one that we just created, and we can see that it only exists in worker one. But if you saw what I did, the kube config where I applied that was to the child, so to that worker. But I'm running this against the parent, and that's giving me an ability to kind of reach into what's going on in the cluster, what's going on all the child clusters, in order to kind of tell me what pods are running and tell me where that hello world's running. So that's quite interesting. So I've kind of got a control plane of all control planes now. So what about kind of propagating a deploy through all of them? So let's have a look at an example of a propagating deploy. So we've got our one here, which see, let's scroll up a little bit. So we've got propagating deploy. So our deployment here of our pod. And we've got a propagating policy that I'm going to specify. So I'm going to point at the test one deployment, which is here. So normal kind of selectors that you might use. And I'm going to say, I want this pod replicated to these three workers. Now, there's some different alternative kind of replica scheduling types. You can do distributed, you can do but I'm going to use duplicated, which is going to mean that I've got should have three replicas inside each of those three workers. So with a bit of luck, let's see what happens when we actually apply that. Second to sync. So let's get the pods from the using the worker config. So this is again using the kubectl of worker one and getting the pods that are running. So this would be as if I were a tenant of that cluster. And I can see that I've got three replicas of that test one deployment that are running here, and they've been running for 12 seconds. So that worked. And similarly, I could do exactly the same for worker two and see the output there. And I can indeed, if I go back to my parent kind of cluster, I can see I should have this is showing me the deployments and showing that I've got test one in worker three and test one in worker two and test one in worker one. So cool. I've now managed to demonstrate creating a deployment in the child cluster and also doing that in the parent and then the parent cascading it down, which all worked surprisingly well. He says having absolute faith in his own abilities and how the whole thing hangs together. Awesome. End of demos. Happy days. I can now relax a little bit, see what else I can mess up. So in that, we saw a cluster of clusters, with an administrative control being carried down to the tenant clusters. And we saw that there was no sharing of any network worker nodes, but still some consolidation. So ultimately a strong isolation. Our last visit to our multi-tenancy emitter shows that it is now well in the red, however. So what's needed to run that in dollars? Well, we need $51. Well, the control plane node that we're using doesn't cost us anything with our particular cloud vendor choice. We have to be using Akamai, what was Linode. So you don't pay the control planes for a non-highly available one, but pick others, and obviously you'll have a control plane cost of running those. There'll still need to be at least one node per cluster, though, in order to support the agent that's running there. So that totals out about $612 or about $12 per tenant per month. So by means of review, we started with kind of basic Kubernetes. We added some multi-tenancy through namespaces. We then added some isolation with node pools, giving some isolation. We saw what happened when we added in some common things like monitoring, logging, storage, CI/CD, and ingress, and some other CNCF logos. And of course, we saw the cost implications of those choices. So we saw the cost ranging from zero for the hierarchical namespace controller with vCluster in at kind of middle ground at 252, and then Karmada coming in at $612 a month for our same kind of empty cluster use case. On top of that, there's the cost of a dedicated ingress for each of those 50 tenants. So bringing our totals to looking something like this. Now add on some monitoring and logging, it will look maybe a bit more, and of course any other tooling, and you can start to see the exponential cost mounting. Some caveats to those costs, of course. So that's the dedicated ingress. Well, what if we dropped that requirement and we had a single ingress controller? Well, Karmada obviously needs one per real cluster, but we can share one with vCluster and the hierarchical namespace controller, which gives us a slightly more balanced result on our multi-tenancy emitter. So a full recap on everything that we've kind of covered today. So we saw that isolation comes, but at a cost. Only you can be the judge of where you want to shoot for on the multi-tenancy emitter. Hopefully we've covered some of the detail that will allow you to make a more informed decision. We looked at some of the common things folk tend to run in clusters and want to be different, such as ingress controllers. And we saw how there's some baseline costs, which some linearly increasing and others ultimately can lead into exponentially increasing costs that can be a real gotcha. And we looked at some of the tools that are along the journey of how to manage something that has something resembling the ergonomics of a multi-cluster, but fundamentally has the limitations of a single cluster under the hood. Oddly, again, these slides got smushed, but we'll run with it anyway. So then we covered Karmada, which is one of the many products in the space for supporting or kind of wrangling multi-clusters. Finally, a big thank you to Loft Labs for hosting these 3 sessions with us. If you've not seen them, then I'd consider Daniele and Salman's talks to be essential watching. So absolutely go feast on those. And a special big thanks to Salman, who's hopefully been furiously working in the background to support this session by hopefully giving me some well-researched or pranked answers to any of your questions, to at least give me some hints. So I'll use that as an opportunity to blame him for any misinformation I'm about to peddle. Again, thank you so much for your time. Hopefully we've got time for questions. If you didn't get a chance to ask it or you're not watching this live, please do drop a line in the Loft Lab Slack or hunt me down on LinkedIn as well. Thank you very much.
Awesome, Chris. Thanks so much. Yeah, we have a couple of questions that I can bring up here. Been answering some of them in the chat too, as everyone's been asking. So, I had a question: Is a tenant the same as a pod? And we have a follow-up question on that, like in relation to what you were presenting.
No, I guess it's the short. No, tenant's not the same as pod. So the term tenant refers to a group or an entity. So take it like a team, department, or project. Includes all the resources for them, which could include pods, but also services, ingress, and everything else. But yeah, the pod in this sense is a Kubernetes parlance of a pod, and a tenant is not a fundamental kind of concept in Kubernetes, or at least not vanilla Kubernetes.
And then, like, if you're thinking about it in like vCluster, you might be thinking of it more as in like a vCluster that's been deployed. So it's kind of a namespace, but then it's the vCluster actual kubeconfig and configuration. Like you might give that to a team or a single person, and that would be like multi-tenancy as a single person or group. All right, so we had a follow-up question. How do you define a tenant? I've heard it explained as a user, a group of users, or an application. I think you kind of answered that, but I don't know if you want to expand on what you just said a minute ago.
I mean, we looked at the different ways of like actually how do you define the tenant? To you, and that the ways that in which you carve your estate, like threat model it, I guess is the really rubbish poor answer. I feel like an architect when I start saying it depends, which is a rubbish answer, but fundamentally it does, which is annoying. There is no hard and fast rule of what is the right way to shard and cut up your cluster and your estate. So what is the right answer? Same thing applies to any other kind of things apart from in this sort of space of you've got a great big kind of thing. How do you cut that up? And the part all of this kind of largely pointed at the tools that you've got in order to create those multiple tenants in a given teams and applications the right level of autonomy to move at the pace that they're going to move at, and also to meet some of your kind of security and management or balance all of those things. So you could have like an application that wants to use an emerging version of like your ingress controller, or wants to use a service mesh or something. You don't necessarily want to operate on that on the entire cluster because that would be quite painful, and you're not necessarily ready to roll that out. Some of these kind of patterns of how you can coexist that while still kind of having some oversight, the kind of the things of what a lot of these bits of tooling are useful for, without having to kind of, as I've referenced, go down the route of the kind of doing Kubernetes the hard way every single time and having a massive burden, because that's no fun having done it.
It's basically however you want to define it is what a tenant is, right? Like depending on your configuration and what you need to set up. Like a tenant could be like a couple of clusters that you've given to a team, or it could be like a single vCluster that you've given to a team. Or all right, so we've got is it a namespace? I mean, like I said, it kind of depends on what you want to define it as. It could be a namespace to separate them, and then they're their own tenant, but it's a little bit different than like if you go back to virtual machines with OpenStack and stuff like that, where you have an actual thing that says tenant, so you know exactly what it is. Is there a demo cluster to see the cost and load? Well, like Chris did, you could install kind. It's not going to give, maybe install kind or install like K3s or something like that on a cluster, and then install vCluster into it, and you can kind of see what kind of load and stuff. Or Talos, yeah. I think we've seen a couple of questions about Talos recently. I haven't actually used it or messed around with it with this, but I think everyone maybe I'll have to make a video about that soon and mess with it. All right, let's see some other questions. We had some vCluster questions. We kind of answered that. How is isolation for each namespace? How is it done? How do you control communication? So if like with vCluster, you can do like isolated, which will make it so that they can't communicate between the two. But in general, if you're talking about Kubernetes, Chris, how would you isolate each namespace?
So, I mean, yeah, you mentioned like using the isolated tag in vCluster behind the scenes. That's going creating network policy. Yep. Behind the scenes, that's then relying on that your container network interface, like the network that your containers are sat on, is going to support that. Pick flannel won't do it, right? So if I did that in that kind cluster, the isolated would have had no effect. The pods would still talk to one another because I think it still uses flannel. Or similarly, like kind of any sort of cluster that I'd done in that way, or pick different ones. Like they'll have their own different CNIs will have their own bits of properties. If they do support network policy, then happy days. If they don't, but they have other ways of sharding, then yeah, you might not be able to attack it with kind of the Kubernetes vanilla tools, which is network policy. You might be able to kind of carve up the estate in other means. But it all depends on kind of what's under the hood. The vCluster implementation assumes that you are on a CNI that supports that separation.
And I think like unlike previous platforms, Kubernetes kind of easy to install, and then it's a lot harder to use once you figure out like all these other things that you need to configure and set up, right? Like whereas other things it's front loaded, and then it's like, oh, it's pretty easy because it shards everything for me. This doesn't. I need to do some work. So we have another question. Can you attach and run the Traffic Hub agent inside vCluster or Harbor and Longhorn? So you can install CRDs into vCluster. Like that's kind of the idea. So say you're running a base cluster and you want to test a new configuration, you would set up a virtual cluster and deploy things into that and see if these new versions work. Like say you've got a new version of Traffic Hub, but also your users can install CRDs and you're not managing those CRDs on the base cluster anymore. They're being managed within the virtual cluster. And these can be production, but a lot of times they're ephemeral environments where you can just kind of bring it up, test, and then just delete it in a shorter amount of time than you would bring up a complete cluster. I don't know if you want to add anything to that, Chris. If not, I can go to the next one.
No, absolutely, yeah. Nothing really to add to that.
All right, so how much extra load should I expect with vCluster? Is there an upper limit on number of vClusters besides hardware limit? So the load is going to be, so with the open source product, the load is going to be like a pod that's running the virtual cluster. And so every virtual cluster that you're running, you're going to have like the pod and then the storage backing it and stuff like that. But with the pro product, what you'll have is you can actually have all that on the control plane, and then you can run just your workloads. Yeah, okay, so that kind of answers. Yeah, so we have some stuff that kind of shows some of performance testing and stuff, but really it's just going to be vCluster plus a pod on there, and then everything else is just running on the base cluster. So like say I deploy an application into a virtual cluster, it's running on Kubernetes on the base cluster. It's just kind of abstracted away from my user that there is a base cluster. They just think they're running on their own cluster. All right, so document, I don't know if you want to add anything to that. It's kind of just, yeah, so I would say like with the pro product, like we thought about that because some people may not want to run an extra pod on something that's running GPUs. They want to run only workloads there. So the idea for the pro product is you move all of the vCluster stuff off and then you're just running workloads. All right, so next question, documentation questions. Where can I find a list of the CRDs and their descriptions for vCluster? So vCluster.com, you can go there and then you'll be able to find our docs and everything. There are things under the generic sync, which will show you some of the things that you can sync between the clusters, but generally CRDs that are going to run on Kubernetes will run in vCluster. There can be some weirdness if you're running like a super old version of Kubernetes or something like that where it doesn't translate correctly and you're running like a brand new CRD that can't be reconciled on the base cluster. But for the most part, if you're running like newer stuff and you just want to install like a CRD, and it should run on there. But yeah, list vCluster docs. I believe if you go to the open source side, you can look under. Actually, just go vCluster docs and look for the generic syncer or under sync. So look under sync, and that'll show you some of the stuff that you can sync between them. All right, one more question. How would the pro product work with a managed Kubernetes service like EKS, which abstracts the control plane? Oh, so I think the confusion for vCluster and stuff like that is it's not like a virtual machine or something like that. It's if you're looking at vCluster, it's like running an application kind of in Kubernetes, like the OSS product. You're just doing like a Helm deploy. So as long as you can deploy something into Kubernetes, you can deploy the vCluster, and it's standing up a pod that's running K3s and a couple of other things. So it's using Kubernetes and Kubernetes. So like I said, with EKS, you can just deploy it in, and you might have to set up some configuration for access to EKS's storage. So you need to give it permissions to be able to create storage behind it so that it can save state. But besides that, it just kind of runs like an application in EKS. I don't know if you have anything you want to add, Chris, to the things that I'm just kind of going through them real quick.
No, I mean, I've done the overhead things. I guess there's the points around that you will have limits on the number of pods that you can have, a number of nodes that you could have potentially in the cluster. So if you were to kind of go crazy and have a really big, massive vCluster estate with a single parent cluster and loads and loads and loads of tenants, you might hit some of the fundamental limits that at the end of the day, those are pods and those are nodes attached to the parent cluster. If you are creating node pools for each one, then you may have kind of big bits of gaps still in your workload nodes, which maybe you wouldn't want. Maybe that's more expensive. But you will still have the limits on number of pods per node, number of nodes per cluster type things to kind of be aware of that might hurt you. And if you are leveraging the thing of like propagating stuff into those tenants, so maybe you want to apply some policy or some rules or some other bits, things that are fundamentally create some workload, or operators and things like that, then that again can have those can eat up your pods kind of quota that you can have across the entire estate. So you may find yourself in that sort of world, have it kind of running out of the overarching design of what Kubernetes kind of gives you a bit sooner than most normal folk would do if they weren't doing multi-tenancy. If you're running the cluster yourself, you can tweak some of those numbers and change the actual limits in the API server and things like that and manipulate it. If you're in a managed one like EKS or whatever, then your configuration options vary, and you may or may not be able to change the number of pods and nodes that you can have in a cluster and the scale that you can get to.
I'm hearing better optimization, and I'm using all of my cluster instead of just a little bit of it instead. All right, so let's see. I get a couple more, and then I think we'll move some of the questions to Slack or something like that. If you have follow-ups or if someone wants to, they can reach out and we can do like a demo or something for them too. All right, let me read this one real quick. All right, sync secrets is going to be a little bit more advanced. It's going to be like the syncer stuff. Our docs, if you look at like the syncer and some of the other things, you can look at like secrets, but it's going to be a little bit more advanced, I think, than we can go over in this right now. Let me see. All right, so can we have a first production cluster which can be copied and deployed on top of an empty production cluster, wherein vCluster is doing the sync of all the data from the first production cluster with all the logos related to Kubernetes without our workload? So if you template out your production server, then yes, you can deploy a similar configuration into vCluster, right? Like say you're using Argo or something like that to already deploy all the things that you need on a cluster once it's set up. Then what you can do is instead of deploy that to your production cluster, you can get the kube config from a virtual cluster and deploy it there too. That's kind of one of the use cases too, is to test, all right, will this new configuration for like my cluster work? Will like the CRD work? Will the CRD break? And that kind of thing. Or will my application break with the newer version of the CRD? When we create the cluster, the controller, and we have some, check out our docs for diagrams on vCluster. We have a diagram. Let me post it into the chat. This will make it a little bit easier. But yeah, I think Chris, we're getting close to time. Do you think have any for other questions? Join us on Slack and ask them. Some of these are a little bit more advanced than what I think we can go over in the video, because it's going to be like linking to documentation and talking about like what you would actually need to configure. Like there are some CRDs and things that you're going to configure that may need you to do some work with the generic resource syncer, because we have a list of things that we sync normally, but we can't have it for everything. So like say you're using like crossplane or something like that, or some advanced other things like CRDs that are a little bit more advanced than just like ingress or something like that, then there's going to be some configuration that you may need to do that goes beyond that. But I think we can go ahead and wrap it up. And if there's more questions, like I said, join Slack, let us know and reach out. And then some of the questions too might be able to follow up with like a video, or in 2 weeks, like I said, we're going to have another demo where we'll dive into vCluster Pro, and we can probably answer and show some of that compared to what we can do now. But thanks so much, Chris. Do you have any parting words or anything else that you'd like to say? Or
No, not at all. But to say, but earlier, like, yeah, go check out the recordings of Salman and
yep.
Daniele's talks. They were both fantastic. Yeah, definitely essential watching. And yeah, I look forward to the pro demo in a couple of weeks.
Awesome. Yeah, we'll have this video too. So if you missed anything on this one, it'll be on our YouTube channel. And then, like I said, we'll follow up with an email with the link to this and then information about the demo next week. But yeah, all 3 videos will be on YouTube. Go and watch them. Comment on them if you have questions or something like that. Oh, hold on. We did have one question that I did miss, Chris. Are the manifests and stuff that you're using for the demo available anywhere? Are they on GitHub or...
I believe he says this boldly, not actually knowing the definitive answer. There is a blog that Daniele has prepared, and
the blog. Okay.
I'm just looking at it now, and I think it has all of the code that I've referenced today in it. Pretty sure it does. If it doesn't, I will make sure it's updated to include it, because like otherwise it will just die and rot. So yeah, it may as well go there.
All right, let me put that to everyone too. There's I think that's the blog that we were talking about. Yeah, that basically shows the presentation, and it has information on what was created and the demo stuff. Cool. All right, awesome. Thank you so much for joining. Like I said, we'll have a video of this should be up today, and then we'll email you with information about that. But thank you so much, Chris.
Cool. Thanks
everyone else.